Hello there. In this video we're going to revisit the central limit theorem, which is one of the most pivotal theorems in all of statistics because it really connects both data analysis, statistics, and probability theory into one common thing. And it also has a variety of different applications in those fields as well. So let us first begin by stating the central limit theorem and what we plan to do with it. So we're going to consider a sequence of identically distributed independent random variables. So independent identically distributed random variables. So the variables are independent from one another and they come from the same distribution. So they have the same exact shape. Whose values are going to be represented by AK. So AK represents the particular data point for a particular sample, and they're coming from a population P whose mu is going to be defined to be mu x, whose variance is going to be represented by sigma squared x. And of course, we're going to define the random variable x bar to be equal to 1 divided by n times the sum from k is equal to 1 to n of these independent identically distributed random variables. Then the central limit theorem says the following three things hold. So we've already proved that the expected value of this random variable x bar is equal to, well, an equivalent representation is mu x bar, is actually equal to mu x, the mean of the population. 2, the variance of x bar, which is equivalently written as the variance of x bar, VAR, is actually equal to the variance of the population divided by the sample size, and which we've proven these two in the previous past when we looked at the expected value and variance of x bar. Now in this video we're going to prove this statement, namely the distribution associated to random variable x bar actually converges to the normal distribution. So that means regardless of the distribution of x, the distribution of x bar will always converge to the normal distribution, under some assumptions, of course. So this is going to be the main focus of this video, and we're going to give a pretty much sketch of the proof for this consequence, so you can sort of get an idea of that it is actually valid. Alright, so our goal is going to be to prove that the distribution of x bar will converge to the normal distribution. So what we're going to do is the following. So remember that the characteristic function, or the moment generating function for a random variable x, and also the characteristic function for a random variable x, sort of characterize all of the moments in a particular distribution. So if you know the moment generating function for a particular random variable, you practically know what the distribution actually is. So what we're going to do is show that the characteristic function for the random variable x bar actually converges to the characteristic function for a random variable z of t. And remember, the characteristic function for a standard normal random variable is e to the minus 1/2 t squared. So our proof is going to be centered around the characteristic functions. And why are we doing this? So let's just restate that. So since phi encompasses all properties of x bar, the distribution also is described in phi. Alright, now for this proof we're going to assume a couple things. They're as follows. So we're going to assume that the mean is equal to 0 of the population, and we're going to assume that the standard deviation is equal to 1, so that therefore we can converge to the standard normal distribution. If you assume for any general mu, any general sigma, the proof is going to be parallel, except there's going to be a couple more little details that you need to assume. Now, there is another assumption that we're going to assume, but I'll explain why we need that assumption once we get to that little step in the proof. All right, so let's begin. So let's first off start by stating what x bar is. So x bar is, again, 1 divided by n times the sum from k is equal to 1 to n of x sub k. And we're going to assume that these variables xk are identically distributed and independent random variables from some population with mean mu variance sigma squared. All right, so recall some properties for characteristic functions. The first property for characteristic functions that you should know is that the characteristic function of the sum of random variables x1 and x2 of parameter t, is equal to the product of the characteristic function of x1 times the characteristic function of random variable x2. And the second is in regards to scalars. So the characteristic function for a times the random variable x of t is equal to the characteristic function of x evaluated at at, where a is assumed to be some real number. And also remember what the characteristic function for a random variable is. This is defined to be equal to the expected value of the random variable e to the I x t, or the itx, where t is a real number and I is the square root of -1. All right, so let's construct the characteristic function for the random variable x bar. So the characteristic function for x bar of t, by definition of x bar, is the characteristic function for 1 over n times x1 plus x2 plus all the way down to xn of parameter t. So we're going to withdraw this constant into our parameter using our properties of characteristic functions. So this is going to be equal to the characteristic function for the sum of random variables evaluated at 1 over n t. And now we're going to use the product of the sum of variables for characteristic functions. So that's going to be equal to 5x1 evaluated at 1 over nt times 5x2 evaluated at 1 over nt times all the way out to the last variable xn. So phi xn evaluated at 1 over nt. All right, so now we make a couple observations about our random variables. So the first, so since x1 and x2 are identically distributed, we know that 5x1 is going to be equal to 5x2 is going to be equal to all the way out to 5xn. So we're going to define each of these as just phi, or you can call it whatever you want. I'm just going to call it phi x. So therefore, that means 5x bar of t is going to be defined to be equal to 5x of t, or 5x of 1 over nt, times 5x of 1 over nt times all the way out to 5x times 1 over nt. So we have n of them. So this is the first, this is the second, and this is the nth term, and this is all that's in between. So I have n common factors, so we can just compress this. So phi x bar of t is going to be equal to phi of x of 1 over nt all to the power of n. All right, great. So that's an important step. So now let us use the definition of the characteristic function in terms of the Taylor series representation. So this gives us phi x bar of t is going to be equal to, so this is going to be the sum from k is equal to 0 to infinity. So we're going to construct the Taylor series for 5x is pretty much what we're doing. So this is going to be 1 over k factorial times 1 over n of it raised to the power of k raised to the power of n. So let's look at this Taylor series in term by term. So phi x bar of t is going to be equal to, so we're going to have 1 plus it over n plus 1 over 2 factorial it over n squared plus 1 over 3 factorial it over n cubed plus and so on. All right, so we're going to have all of our terms here. So let's just write out a couple. So phi x bar of t is going to be equal to, so what I'm going to do is I'm going to focus on this term and this term only, and then I'm going to group all the rest in another term. So we're going to have 1 plus, so I squared is going to be -1, so actually this is going to be a minus. So this is going to be t squared divided by 2n. So this term here is a complex term, the next is a complex term. So we're going to group it and all of its following terms in a order series. So this is going to be plus O star of t cubed over n cubed. N. So this is going to encapsulate all imaginary terms and all real terms of order 3 or higher. So this is where that other assumption is going to be important. So we're going to assume that the third moment and higher for xk are finite. So we're going to assume that the moments above 3 or and above are finite so that we can send n to infinity and this term converge to 0. If you don't have finite moments, there are a couple awkward things that could happen. We'll definitely consider them in later series when we have some more advanced calculus tools behind us. So now what we're going to do is we're going to send n to infinity. So that means phi x bar of t is going to be asymptotic to the curve 1 minus t squared over 2n. So this term is going to go to 0 as we send n to infinity, all to the power of n. So now let us look at these terms in terms of n and see where they go as n goes to infinity. So we're going to rewrite this. So phi x bar of t. So we're still taking the n that goes to infinity. We've just taken care of that term. So this is going to be asymptotic as n goes to infinity to what? So this is going to be 1 minus, so we can rewrite this as 1/2 t squared divided by m, all raised to the n. Now there should be a property that you should have learned in calculus which says the limit as n goes to infinity of 1 minus a over x or a over m raised to the power n is equal to e to the minus a. So if that is the case, we have that this will converge to e to the minus 1/2 t squared. And this should look familiar. This is the characteristic for a normal random variable with parameter t. So what we've done here is we've showed that the characteristic term for x bar of t converges as n goes to infinity to the normal random variable characteristic function phi z of t. Now, of course, this assumes that all of our variables are independent and random. And what do we mean by n goes to infinity? So n is the number of samples. So if we continue to gather sample after sample after sample after sample, and they're all independent from one another and identically distributed, satisfies all your properties, then the distribution of x bar will converge to the distribution of the normal distribution. So it doesn't really matter what type of distribution you had. It can be heavily skewed right. Of course, you won't see a normal distribution until n is really big, but eventually the distribution of x bar will converge to a normal distribution. And then you can use properties on that distribution to approximate properties of the sample mean. So that's just a sketch of the central limit theorem proof for the special case that the mean is 0 and the standard deviation is 1. You can easily generalize that to higher or more general functions, of course, but this pretty much is the general proof of the central limit theorem via the definition of characteristic functions.